All right. Hi guys. So, yeah, this stream today is just me rolling the camera while I'm preparing some stuff. And so if you have any questions or so, you can ask. It could be that I maybe missed something because yeah, it's not that I prepared something for today, just my usual stuff what I wanted to do. And yeah, so that's about it. So what I wanted to do today is do a little bit of preparation work because I got a lot of questions which are more or less mostly the same. And the questions I got the most, I would want to take them and maybe put them into a video later on. And for that, I wanted to prepare something. Yeah, so let's get into it, right? Now, just preparing some bit of music here in the background. I think I cannot share my Spotify music because I think the stream will get taken down without notice. But yeah, put your own music on. So, yeah, one of the most problematic things to understand or get, which is rather easy, I think, and that's why I think this would be a great video, is about symmetry constraints. So symmetry constraints, they work differently on Inspire and Hypermesh. Maybe to get that a little bit deeper, or yeah, to have a little bit more context, is Inspire and Hypermesh are doing things differently. For example, for symmetry constraints, and you the general way is that Inspire lets you do more easily, and Hypermesh requires you to understand more before you can apply it um, correctly, I should say. So in Inspire, there's just easy click solutions. So one click and you have got everything. And for Hypermesh, there isn't. It's rather expects you to know the stuff, and it's good to know them, even also if you're using Inspire, because yeah, just makes sense to know what you're doing. And yeah, maybe we can do that a little bit. And then I think also what's something which is really bothering a lot of people in my from what I see is TCL scripting. So that's a huge topic, and I mean I laid maybe a little bit of a foundation with some easy introductional TCL scripts, but for sure you can take that a lot more way, and we can see about that. Yeah, so but now let's get into it. So I downloaded the newest Inspire model, or Inspire version I should say, and I try to do something with that here. So let's just do a simple sketch here. So something like we did a multiple of times, just to test it if we still know what we're doing. So I don't like the unit system. I always use MPA mostly. Um, all right, so this is it. Now right click and be done with it. No? Oh, it's so strange. I right click here, it's my second monitor, right? And it's not just not working, it's displaying the the content on the main window. Really, that's alright, it doesn't matter. So scrolling is a bit tedious here. Okay, extrude. It's all German, right? I should maybe change that. Get a little bit of bending here. Hey, they abandoned the right click swipe left to complete something. Okay, let's see about that. Now, I think we can go with standard steel here. That makes sense. Then let's go for structural I have to change the language. Sorry about that. Man, that's so stupid. Really, that's a bug. I right click, I click anywhere here. It's a second monitor. It's nothing fancy. It's just another monitor. Um, because then I can share the whole monitor and don't have to be bothered with sharing windows, because then you cannot see anything with context menu and stuff. But if I click here, it pops up on the second monitor. Um, okay, English. Yeah, you know what? We will maybe do that again. Let's restart Inspire. Maybe then it works if it starts automatically on the second monitor from the beginning. Maybe then this works. No. The loading screen was there, but the main window isn't there. Okay. But now, let's see. Okay, maybe it fixed it. Let's see with the preferences. Yeah, okay. Now, let's do that again. So we were geometry, sketch, new sketch, select the X kernel plane, and just draw something. Okay, it's still there. Okay, yes, I know that. Okay, then geometry, extrude. Let's do 500. Okay. I think I didn't saw the check mark because it also was popping up on the first monitor. All right, now we have our little structure where we can test things. Now I have to go into implicit modeling at some point. That's pretty interesting. Yeah, but not for now. For now, I just want to do simple stuff. All right, not connectors, but I want to go for what? Setup should be here. Yeah, supports. Just bothers me that it's saying loads here. Yeah, it has everything. Yeah, all right. So just support that. I'm also, this is something which bothers me. It just puts some random location here, right? So it's not a center, it's nothing, it's just random location. I'm not a fan of that. All right, then maybe put little force here, kilonewton maybe, and put it. Yeah, that's also a cool trick, right? You can just double click on here to change direction. You don't have to put a minus here and press enter like I did before. All right. Now, this would be a full model, right? So this would be a full model. There's nothing with symmetry or so. It's just a full model. If I take this, copy and paste it, put it down, and yeah, I'm just messing around here, right? So don't take it too seriously today. So geometry, and then there's trim split. So I could trim. I would like to split. I think this is also changed. Cannot remember that it would be like this. And there you have to do a tool. Okay, I want to split this part. Tool. I don't have a tool. I want to split with a plane. Huh? Maybe another option. Yeah, maybe slice. Yes. All right, this is it. Now I have to, I could now delete 1/2. And I'm doing the same stuff here again. Same stuff here again with the constraints. Now structure, constrain one side, and put how much force here? $1 million question. Should be the half of it. There's also something, it's also a point a lot of guys miss. if you do a symmetry constraint, you also have to decrease the load accordingly. Because if you just think you have half the structure, that means half the stiffness, and you put the same amount of load, you get double the displacement, and that's not what you wanted. So bear in mind that if you do a symmetry constraint, something like this, then you have to look for the loads. Gets even more complicated, to be honest, if you're talking about a multiple point constraint, MPCs. Because where should the master node of the MPC be with symmetric loading? It's not that easy. Yeah, just think about, do I have a... I don't have a paint here. Just think about something like... Think about something like you would have, this would be the whole structure, and there's some area here. That's not a hole, it's an area. And you would like to do a multiple point constraint here and have it perfectly in the center, and then you have your spider all the way around to all of the nodes, right? If you do this on a symmetry model, like so, should the master point then be still at the center? Or should it be at the center of the new surface? It's a tricky question, and I struggled with that myself, to be honest. I thought it should be at the center, because that's what's happening, right? But the reality is that you're introducing a bending moment. And this is not something which the symmetry constraint will cover. So just think about looking from this side. Rather, yeah. You're just getting a bending moment around this axis. And symmetry constraints are like this, that they prevent any movement perpendicular to the symmetry plane. But a moment here, that will get transferred. So the correct solution is to put it in the surface center of the new nodes, even if that seems odd, because the load application point changes from the non-symmetric to the symmetric. But this is a balanced force situation, and the other one would not be a balanced force situation, right? Because what exactly is the force doing? It's moving it here down, so into the screen with the top view. And yeah, that's not that good. All right, that's for a little thing here. Now, if I have now two models here, I think I can do that both in one model. They may not be accurate, but just to see if the difference are working, I think that's fine. Now, to get this to be a topology optimization domain, I have to check the design space on both of them. Yeah. And now, if I'm about to introduce some boundary conditions for symmetry, I think that's in the shape constraints, shape controls, right? So I go here, symmetric. Yeah, this is exactly wrong. This one. To be honest, now when I'm thinking about it, just think about this one. This model is a full model, but there's a symmetry constraint in the middle. So that means it will get... There will be a symmetric model. But there's no way I can get that same thing with the lower model, because if I select this... let's try that. So for sure I don't need this, I don't need this. But now can I move that? Yes, I can. So I could move it. Could move it to just this point. That's pretty interesting. If that will work. If that will work. Okay. Let me duplicate that again. That would be interesting. Oh, sorry, did I not? Have I now too? Yes. I would have liked to move the other one. That's stupid. Let's do it like this. And move that down. No. Just this one. Move is M key, in case you're wondering how I got that tool. You can also click on here. That would also work. What the hell? Okay. This belonged to the move tool. Alright. Okay. But I think I have not duplicated more than once, right? Hopefully not. No. Alright. Now the lower one, I would like to do that manually. I like to see if that's doing exactly what I think it's doing. So go again for the constraints. Same thing. Also here. And now let's just make a complete symmetric boundary condition. So now this is where it becomes interesting. What you have to constrain here, I always have to see which one of the buttons it is. No. I think it's not even a button. You have to click on here and then go to View, Property window. Nothing. Let me save that model, because now we have some decent progress. Inspire. Test. Alright, let's see. Why isn't it showing a property? Property window. Okay. Now, this constraint is now locked. It's locking all surface nodes in all translations. But I would want to have it just locking the perpendicular movement, which is Y. And I cannot really constrain the rotational degrees of freedom. Does that make sense? Yeah, I think that makes sense. Because we're on 3D and every rotation of those points as a whole, they would result in a translation. So I think that makes sense. That makes sense. Now we have three models, right? Three simple models. A full model, a symmetry model with constraints, and a model which we did on our own with symmetry constraints. It's a lot harder in Hypermesh to do this. But yeah, doesn't matter. Let's see what it gets us. No, it's not. It's structure and then optimize. And now let's see what we're doing here. We're doing a stiffness optimization because it's easy, and we take maybe 25%. That's okay. Let's just go with the defaults and run it. Yeah, I know. Supports or rigid connections share common features. Yeah. That's not a problem. Alright, let's see. Yeah, prime time for streaming, right? Saturday morning. I think for America is still nighttime. Or early morning. Yeah. Yeah, it's on the weekends. But I think, yeah, it's just the way it is. I'm not a full-time streamer, so I think that's fine. That's fine. Could maybe also look a bit in the run history file if I find it. Oh, it's done. Okay, but I have it on. I have it also open. Ah, by the way, which solver did we use? I think we used a SimLab solver. Interesting. So the top result, that looks plausible. If we would mirror the second solution, that would be a different solution than the one from above. Right? That's not the same thing. And our own solution doesn't work. Really. That seems so stupid. But to be honest, it's not fair. It's not fair to be honest, because those should be separate design spaces, but I don't think I can do that. I don't think I can do that. I don't think I can do that. Let me think. Let me think. Can I do something which separates the design space? If I could do something, I would suspect it being in the in the model editor. But I think there's just a design space option here. All right. First, I have to go back to the geometry. So design space. It just says design space. Yeah. Maybe I have to do it separately. Yeah. Don't like it that much, but yeah, I think I have to. The thing is, because I have a constraint of the volume, which is for sure the whole design space, and that doesn't make sense to not constrain it for different models individually. I think I might be able to get away with it if they would have the same volume, but they don't. So they don't. That's a problem because the upper one has more volume. Yeah. All right. Doesn't make any sense to keep complaining about it. Let's just delete those two models. Just start again with the full model. Now optimize this and say that would be the full model. Full model. And let's go with 25 again. Yeah. Just make that the same for everything. Thickness constraint, minimum 80. I mean, this determines the mesh size, so this also determines the speed. And it's also very important to notice we are using the SimSolid solver here, right? So we have to do that for the other ones as well. Yeah, okay. So let's do that. So load support connector has been applied to design space. I know that's not the ideal option, but I think that's okay for now. So we can continue with that. So this is the first model. So let's just save that as full model. And we will now run it and see the results. Make a screenshot, put that away. Maybe I can save that to a little PowerPoint. And then we will do the reduced models and see how they're working. By the way, if you wanted to change the solver, that should be somewhere here. Run options, analyze the solver, SimSolid. I didn't know that SimSolid was capable of doing optimization. They must have added that. Okay, so this is your typical bending case. The result, I would say that's very much the expected form. Okay, now let's just simply make a screenshot. And I put that here into PowerPoint. It's also something I would really like as a macro, that it would just take screenshots from every side and save that to a PowerPoint. Sure, there exists something out there, but I don't have it. What? Yeah, that's pretty boring, that view. Just make sure that I get it right. All right. Okay, so that would be the full model. I've just taken those screenshots to a little PowerPoint. And now we can proceed to do the other models. So I think the easiest way would be, I think we saved that, right? To just go back to the model. Yeah. And delete two other models. So that would be a symmetric model, which I say it should be symmetric. And the plane of symmetry is here. It's very interesting to see if that really is the case then. Because I didn't experiment with replacing or moving the symmetry plane with the shape controls. But it's also interesting if you just imagine what that would be, right? If you're placing a shape control, a symmetry plane, which is at the boundary of the domain, it's not really a constraint because you don't have the other side. So whatever design it comes up with, it would fulfill the shape control constraint. So I think this will not be really a symmetric model. Unless Inspire is as intelligent as I hope here and sees that the shape control is at a boundary and then introduces symmetry constraints. But I doubt it. Now let's see. Save that as, this is half model with shape control. And yeah, we will just let it run same way. 25. Oh, it will get a different minimum thickness constraint. That's interesting. We should not do it differently from the full model. Otherwise, we will impact the design right there. So I will change that to 80 and run it. Yeah. Let's see how this turns out. Yeah, it's interesting. Because shape control, just think about what a shape control would do if you would be a alter guy who likes to program those things. A shape control, you would force the density to be the density of the topology optimization. You would force it to be symmetric. That's what shape control sounds to me. But if you have a shape boundary or shape plane, shape control plane at the boundary of your design domain, you don't have matching partners, you know? If you would have this shape control plane in the middle, you perfectly can say, all right, do your optimization, and then the symmetry constraint is like this. I just go and cut with the symmetry plane and just match the densities that they will be symmetric. And you will get a symmetric design which is symmetric regarding the symmetry plane you introduced. There are no additional constraints there, but design or density matching. That's my guess. And that's why this will differ. Yeah, it differs. Let's see. Can I do like a symmetry? No, I cannot. I cannot. It's not a section cut, no. Oh, cannot do that. Okay, let's just do. Oh, wait a second. Stupid song right now. Okay. I cannot do a reflection here, but I can do the symmetry. Edit the screenshots. I have it in the PowerPoint. That's. It's not a stupid design, to be honest. So regarding what it should do, but it's not. It's not the same. Let's say it like this. It's not the same. It's not the same. I will show you a comparison soon in the PowerPoint, and we can compare it one by one. By the way, if you feel like you have a question, a quick thing you wanted to ask regarding Hypermesh, just feel free to ask. It's really, I'm here for fun doing those preparation. And if there's something I can help with, just say it. Okay. All right. So we have a question here. I just got in here. Are you running shape optimization? So now today is topology optimization. Shape optimization in case of differ certain radii or contours of a structure. That's a different topic, but yeah, I might cover that later, but not today. If there's something you have an interest in, just let me know. So if it's maybe a sizing thing or if it's changing the form of a radius or something like this, there are pretty many options of doing shape optimization. So it's pretty big topic. Now, this is the difference here. You can see that center mass. It somewhat has that too. And but this is going from the middle down. And here you have it, you have a thing right here. That's different. So I don't think the shape control did too much here. On the other hand, it looks like that to be a symmetry plane. But it cannot really tell you what it did exactly. So we have to see about that. All right, that's that. I save it and just open the model again and delete the upper two models. And yeah, let's just save it as half model, symmetry, own constraint. And solve that again for 80 millimeters. That it's comparable, 25% maximum stiffness. All right. Also here, I'm not that much sure if the symmetry constraint really is doing what it's supposed to do, because there isn't the option to constrain the rotation really. Or to be more precise, it's the option is missing to not constrain rotation here. if you see at the constraint here, this should be the symmetry constraint, right? It affects all nodes of the surface, and my guess is that this will be held in place by an NPC. But that again also makes no sense. No, I think it will get transferred to the nodes. And wait a second, is this? Oh, that's wrong. Sorry. We don't have to constrain accent set, so it should be like this. Run it again. But it fails to set free a certain point of rotation. But maybe that's also a good point where we can just clarify the thing again. Now, if you have a symmetry plane, let's just make a symmetry plane like this. You want to constrain everything which moves perpendicular to the plane, right? So this is forbidden. Now, let's say we have a coordinate system which aligns with our symmetry. So this should be, but in our, well, wait a second. In our case, it's y. So let this be y, let this be x, and this be z. Now, we wanted to constrain everything which has a y direction of movement. And that's where a lot of people get stuck. So we have our DOF 1, 2, 3, 4, 5, 6. Which one should be constrained that we have no y direction movement? The first one, which is obvious, is this one, because that's y translational. So that has to be fixed, right? That makes sense. X translational doesn't really result in a y directional displacement, so that makes no sense to constrain it. So this should be free. Z translation, so that would be up and down. That's also not affecting y displacement, so that should be free as well. Now we have 4, 5, and 6. 4 would be X rotation, right? That would be something like this. And the rotation around X certainly causes a y displacement, because just think of a point. If that has to turn around the x-axis, it has to move towards y. So that should be constrained, right? That would be x rot. Now 5. 5 would be y translation. Y rotation. Rotation around y. And this would be all on that plane. So there's no y movement here. So that means that can be free. And Z rotation, you're talking about rotation around the Z axis. Same thing as with the X rotation. You have to constrain it. And if you noticed, you can see a pattern here. You constrain the displacement, which is perpendicular to the plane. And then you constrain the other two rotational. So 2 would be y translational, and you also constrain x and z rotational. That's as easy as it gets. If we have a different symmetry plane, which would have, for example, a different thing, here would be x, y, z. It's pretty easy. Same plane. You constrain x translational, that would be 1. And then the other two rotational would be 5 and 6. Because a y rotation and a z rotation here causes x movement. Alright? That's how you get that. So, yeah, that's how I remembered it. So you have to constrain the movement perpendicular to the symmetry plane. But you can leave the movement open around this axis, and I have to constrain the other two. Now what Inspire forces me to do is I'm not even able to not constrain rotational. And there's an option here. And for a reason that makes sense. If you just think about a 3D structure, right? 3D structure. Something with nodes here. But 3D, not 2D, right? So, whatever. Every rotation, whatever the rotation is, will result in a displacement of a translation. So you cannot rotate this without moving it in a translational value. Contradictory to that, what could be done is, for example, move NPC around a point. This rotation will not cause a translation because the point stays the same. Same thing with 2D structures. If you have a 2D mesh and just rotate around this axis, those nodes here will stay the same. They will stay in place, but it will get rotated. And yeah, so this is something to take into account. All right, let's look at the results. This one. Interesting. It kind of makes a lot of sense to put everything to the outside and leave it in the inside rather empty. But I'm not a fan of the mesh. Very interesting. Yeah, let's do the screenshots again. And then we switch over to Hypermesh. See how it's done there. Just makes a giant wall here. Yeah. Okay. I mean, if you think about momentum, inertia, and stuff like that, that makes a lot of sense to put it at the outside. And also for bending case to put it at the bottom at the top. That makes a lot of sense. But to be honest, yeah, not so sure about the efficiency. We can maybe look also at the compliance values we got, because that's the measurement of how efficient the optimization was, right? Just finishing up the PowerPoint. All right, now this is what we have until now, right? So full model, shape control, and our own symmetry constraints. All right, now let's get to Hypermesh, and you will notice the difference between how easy it is to do that. Let's check the dimensions again. I think that was 200 by 200 by 500. And we had a 80 millimeter minimum thickness constraint. That's pretty harsh. Now let's just get the average mesh size that we have, something which we can work with. Can I measure from point to point? Wait a second. What to measure? Select the part. Yeah, okay, so if this is 200 and we have 1, 2, 3, 4, this is 25, right? So 25. Okay, for mesh constraint. Okay, now let's switch tools. Where do I have it? I have it here. And also let's make use of some simple TCL scripts. So the tools may look the same initially, but they're very different. Something which I like to use for doing new models is using my library of text TCL scripts. The thing is, why I like this is, yeah, it saves you a lot of clicking. And maybe I should work on that one to do a little bit more, like, yeah, let's see. So this is my GitHub, or part of my GitHub. And there's Hyperworks scripts, create models. And we want to do a 3D optimization, so 3D Opti script. And I will just go to raw, copy all of that. Then go to view TCL console. Oh, sorry, wrong tool. View. Ah, we have the TCL console already here. Paste that in, press enter, and you have a decent thing here. There's design space, non-design space. You have load collectors, load step, material objective, optimization constraints, controls, the responses, the property. Yeah, so pretty much it. Now, let's do the geometry. So that's pretty the same way as in as in Inspire. Okay, great. 200 by 200. Now, geometry. No, it's called topology here. Then extrude, not lines but surfaces. And now 500 millimeters. Okay, that's about it. Now we have to do the meshing. So we go to 3D and we do a hex mesh here. But no, well, you could do a hex mesh here. That would work. But as Inspire using a TED mesh, I will use a TED mesh as well. And for TED mesh, you have to be so careful, really. You have to look at this menu here and check the growth rate and put that to 1.0. That's also one thing a lot of my students got wrong, or constantly get wrong, because it's so easy to miss, and I got it wrong also multiple of times. But let's just think about, we leave the 1.3 here, right? We select the solid, we select our mesh, 25 millimeters, as we would have guessed. Click on mesh, and you have your mesh, and it seems good, and you go along on your day, right? No. Just think about if you go to elements and just hide a lot of the elements, like so, and also make the geometry transparent and shade the elements. Well, it's not that obvious here, but the elements get bigger as they are moving inwards. And that's not really what you want. Because if you have something like that and you do a topology optimization, it cannot really build structures in the inside which are efficient and small. So that's not a good thing. Therefore, pay attention when meshing that you change that to be 1.0. Other than that, we can go with the default values. Another thing is, but I think this is already done correctly here, is in the advanced, even more hidden, right? In the advanced tab, you have to do original component. No, you have to go to, no, yes, original component is correct one. But sometimes it's put to current component, and then it will put it always in the component which is boldly marked in the model browser. And that's also a huge pain in the ass. Because if you have multiple solids, and you want to mesh them all at once, usually you don't want to have that all in the same component, the elements, right? You don't want that. You want to have the elements there where the geometry is already. So solid 1 should have the elements of solid 1. Solid 2 should have the elements of solid 2, and so on. So and that's what original component does. It just checks the component where the geometry is located, and then the meshing process will write the elements into that component, right? All right, now that's about that. We have meshing here. Now, that would be a full model, but with shape controls, to be honest, we would have done the splitting first. So what I missed here is the splitting. Now, if I can do the splitting also afterwards, but it may also upset the mesh, because you just think about it, the mesh is already there. And if you're now introducing a symmetry plane, you're splitting the solid into two, you force the mesher to point the nodes onto the surface. So it has for sure to readapt the mesh. But other than that, it could distort the mesh. I don't know if it does a proper remeshing and stuff like that. So that could be a thing. But normally you do the splitting before you do the meshing. Or delete the meshing, do the splitting, and remesh it again. And yeah, that's about that. Now I think about how should we proceed. I think it's good to do a full model and then split it and do a reduced model as well. Yeah, I'm thinking that makes sense. So meshing would be done for the full model, but I will be splitting it anyway, because I think it's just it doesn't really change that much, but it makes life a lot easier later on. So we split here with plane. The target should be a solid, and that's also something which is, yeah, you have to change it to solid, otherwise you cannot split solids. Then tool would be something here, and it snaps. It should snap to the midpoint, but to be sure, just don't show the mesh, because you see it's also snapping to nodes, and you don't know if that's the midpoint. So hide the mesh, then you will be sure. Okay, split that and split it. Now I will be seeing what it's doing to the mesh. Nothing, right? Didn't really bother adapting it. No, all right. Okay, that's not good. Okay, I will delete the mesh and just remesh it. So again, 3D TED, we can now assume that the options didn't change. So mesh it, right? So you have nodes which are perfectly on that. And that's also good because normally what I think you should have is a symmetric mesh. It looks like it, right? But if you would want to be absolutely sure, there's also an option to reflect around a plane. So that means you mesh half of it and then you reflect it, and then you make sure that you equivalence the nodes. So that's also a thing which a lot of guys missing, because that's easy to miss, and that will completely destroy your model, because you then have nodes which are close together that should be the same nodes but aren't. And if you then put a load onto it and constraints onto it, it will just fly out of the plane. Or even worse, just think about it here. If you constrain it, then both sides and the force on both sides, I don't know why, but just assume we do it like that, you wouldn't even notice that there's something missing in the structure. You would get results that seem plausible, but in the middle is like a knife went through and disconnected the nodes. So it's a completely different structure. And yeah, so you have to be careful about that. And also, I think the nodes, the equivalence tool is somewhat hidden in the new version. I'm not sure if equivalence, it's under the validate, I think, yeah. So yeah, here, validate equivalence. If you just select all the elements and say equivalence, it will look for nodes which are close together below the tolerance and will equivalence them. It should say at the bottom 0 nodes were equivalence, because there are none to equivalence. But as we are at it, let's just try to do this with the symmetric mesh. All right, let's just imagine you want to have a perfectly symmetric mesh. So you create on one side a mesh, and now you want to reflect that. And I also have to see where this is now. Mirror. I would like to mirror around the plane. The plane should be that one. No, should be this one. Y direction, yeah. And I want to have a show preview and keep the original And the elements should be the displayed one, or that one. Yeah, that seems right. More or less. The preview is a little bit funny. Yeah. Okay, now we have mirrored them. But the thing is, what about the nodes here? So it's just I'm rotating it that I have just this edge here. And now let's come up with a panel which requires us to select nodes. For example, let's go to, where the hell is it? This is analyze. I'm getting so confused, to be honest. Inspire, it's called structure, it's called analyze. It's so confusing. Okay, but let's go to, for example, the force. This requires us to select nodes. If I just select here, see, at the lower, I hope you can see that. So it's down there. It says two nodes selected. So that's a reason for us to get panicking. And yeah, so go on validate, and then on equivalence, and then select all the elements, and then equivalence, and you will see 208 nodes were equivalents. Normally it also showed them, like little yellow nodes. Yeah, so you're now ready to go. Okay. Now, we can go on modeling the constraint now. Okay. That's again under analyze. Then the constraints have a different icon here, right? So, and we have to select like nodes. Okay, that's not a problem. We can select that easily by doing something like this. There's other options too. We can constrain anything here, but we can also leave the rotational degrees of freedom away. And I have not clicked OK, so the node selection was redone. Okay. Select the nodes, press OK. And this is what I think would be okay. So I have the wrong SPC collector as current. All right. Now constraints is done, and now we can go to the force. Now force is also pretty interesting how to do this. I'm not exactly sure how Inspire would handle a line load. But my thinking is that it will do something like it distributes it to all the nodes on the line. Eventually that's what's happening. Because I'm staying away from using NPCs here, because we just had the edge, and the edge, if you're doing NPC there, it has there's no lever around a particular axis, and that's a problem. So I'm staying away from the NPC stuff, and we will do just something like select the nodes here and do an evenly distributed load. So 9 nodes were done here. Let's think about how to distribute them, because you have a free edge here. I think what would be appropriate is to select 7 nodes here and do a little calculation. 1000 divided by 7 would be 142.8. So let's do like that. Ah, no, sorry. Sorry, no. I have to divide it by, because that would leave the 3 edges open, and that's not what we would want to do. I think it would be good to have the edges seeing half the load of the other loads. So what is to be done then? We now have to do a little algebra to get that. Am I able to put that through in my head? So what we would like to do is divide the force of 1000 Newton, not by 7, not by 9, but by 8. So 1000 divided by 8 should be 125 here. So let's just think about this. 125 times 6. And then... No, times 7. And then half of it. Yeah, I think that makes sense. All right, so 7 nodes selected. Constant vector, magnitude, direction. Direction would be -1. See, there's no easy set button to click to invert it or so. And the magnitude would be 125. So, and we have to make sure we have the current loads to set to the correct load collector. We can create that. And then we do the same stuff for those two. But here we have 60 to 62.25. No, 62.5. So that's that. Where's my mouse? Where's my mouse? All right. 62.5. Yeah. Okay, I think that's reasonable. Now we have that, and it's not good that they have the same color. Let's make a different color here. Okay, something like this. Now, topology optimization side of things, which we have to do. We have a design component. There's no non-design component, so that's easy. The objective would be minimize compliance. Yeah, that's okay. And constraint, yeah, here I think we have 0.25 in the Inspire model, so we can think about doing that. There's just some simple constraints here. We have now responses to volume frag and awaited compliance. That makes sense. I think we are done. Now let's save that. Let's save that as a Hypermesh model. Let's do there another folder. Full model. So for sure this is OptiStruct, right? This is not a SimSolid solver, but I think for this comparison it's okay. Now we would want to optimize. Go run here. Yeah. Yeah. The material should be the same, it's all steel, so that's not a difference. And somewhat I compromised my running console. It looks like this now. Not sure if I have to do a reinstall to have it the way it was before, but I don't know how I did compromise it. It's just now showing it like this. But it's okay. While this is running, we can definitely also start a Hyperview post-processing window. Oh, it ran already? Wow. Okay, yeah, it's a small model, so let's get a second screen. Let's choose Hyperview for the second screen. And let's just open that, sorry. So with the underscore des h3d, we can get a look at the design or the density. And let's see what the density distribution looks like at 31. Yeah, let's move that a bit. And also let's do an isoplot. So basically what I see here is something different, but not that much different to the ones we got from Inspire. If you just look back at Inspire. Something like this. It's much more smoother, right? There's some sort of remeshing going on. It has finer mesh size. Yeah, because it's SimSolid, that's a bit of a different approach, yeah. You can see that the big knot in the middle, that's definitely there. But what this optimization here does is also putting stuff more to the outside. So that's also interesting. I think there's no symmetry constraint, right? So that's an unconstrained model. Ooh, okay. Let's add a symmetry constraint because that's why we're here. So symmetry constraints are done a bit different here. It's in the topology optimization variable card. And here you have, oh, and I think we also did not do the minimum member size. Yeah, sorry, yeah. There was something like this. And now we have the pattern grouping would be one plane symmetry. And I think, yes, I think the origin is in the middle. So we could just use coordinates. 0, 0, 0 is okay for the origin. And the first grid is the normal of the symmetry plane. Yeah, you see, it's a lot different or a lot more complicated to define. But let me explain it in a second when I started to run. So that's full model, symmetry, and 80 millimeters min member. Okay, let's run that and I will explain how this makes sense. Now, what I did here was to do a pattern grouping, which is the same thing as saying that I introduced a symmetry constraint. To do a symmetry constraint with a plane like this, I have to define in Hypermesh a so-called anchor node, which is directly on the symmetry plane. And I want to have a first node, which is perpendicular to that plane. So you're defining the normal vector of the symmetry plane. And the anchor node, or the anchor coordinates, they just show you where the symmetry plane is located. So origin gives location, and the first node gives direction. So for what we did here was the 0, 0, 0, that would be the origin. 0, 1, 0 would be 1 unit towards the y direction. So in this direction we had here the 1. And that's the normal direction for a y normal symmetry plane. That's why we did it like this. Okay, now I think the run has already finished. And we can also load it in like this. So load it in. That would be this one. Huh? What? Ah, it's not a hyperview. Yeah, you have to change that to hyperview. Now, 80 min member, also the des again. And now it's something cool here. You can right click here and say apply style, current pages all selected. And now you have that here. Ah, you see? Interesting. It's a lot more similar now to what we have in Inspire. Always make sure you have the latest iteration because that can differ. For example, here in the first simulation, we just had 31 iterations. And if you do apply style, all pages all selected, whatever, it also goes to the iteration of 31. And the iteration of 31 look different. So now this looks pretty comparable to what we have, right? That makes sense. So just going that to the full model, this would be the same thing. Yeah. All right. Now, this was to be expected, but now let's see if we can get the same results with a symmetry model. Because we were not able to do that either with the shape control nor the symmetry constraints option, right? So we could not do that. Let me save that model here. And now let's just completely destroy the model. I think because we distributed it, we would have to change just this force to be half of it. But let's do one by one. First, let's go to the solid selector and delete the solid. Which one should it be? I think it doesn't matter. And also delete associated surfaces. Yeah, that makes sense. Okay, but it did not delete the elements. Okay, we have to delete the elements. So go to the elements, select the elements, delete them as well. Now I want to change the force. I go to the load selector by pressing L, selecting the load, and this should be then 62.5 as well. Because the other 62.5 is on the other, not models component, right? Constraints here could be the same, but we now have to have some symmetry constraints. And those symmetry constraints have to be modeled on the surface here, like we did before. But here we can now also constrain the rotations like we wanted to, right? So we can go to analyze constraints. Then, yeah, select the nodes. Let me just let me just show you another way of selecting that by not drawing rectangles. Normally you can also just press Alt. It doesn't work here. Alt is by path, yeah, but it's not that what you wanted. You can do with the 3 dots here, and then not by collector but by face, and then you can select the face. And that's it. So now, which constraints again? Let's start blank. It's the y direction, right? Right, y direction is perpendicular to the plane. So for sure, dov2 has to be 0, and then the other 2, which are not y. So 2 and then 4 and 6, not 5. Because 5 and 2, those are the same thing, rotational and translational. Okay, create this. Now we are set up, and I think that's about it. We could also, yeah, we could remove, and we should do that. We could remove the symmetry constraint here, because that doesn't make any sense. Because yeah, it's on the edge, and I think that doesn't make any sense to do this here. It's per definition symmetric because we only model half of it. Now let's see. Let's save that under a different name. That would be the half model. And run that. Or did I forget something? Oh, I don't think so. Okay, let's run it. Okay, and I think we need another window. Change that to Hyperview. Yeah, in case anyone wants to ask questions or so regarding any topic regarding Hypermesh, it's not a problem. Just put it in the chat. I'm here for a couple more minutes after that, and I think then I will call it a day. Okay, run is through, yeah. So we can load that in. Do the same thing here again. Apply style, current page all selected. Let's check about latest iteration. It's a different design, right? It's a different design. Or is it? Wait a second. Which one did we model? I cannot tell. Yeah, okay. No, no, it's not a different design. I think it's the same. This can be shown here pretty good by doing this symmetry thing with where is this? Ha. There is a thing where we can mirror that, and I just have to find that. It's panel symmetry. Yeah, this is it, but I don't know where I could find it. It says panel symmetry. Yeah. Result symmetry is also there. I think I'm blind. It's not there. Table, whatever. Annotation. Ah, here. Yeah, I'm blind. Okay, symmetry here. Now I can make this a symmetry component, and we say reflect that with, and I think this is the plane now. This should be then the XZ plane or ZX plane. Does it work? Yes. And now we can compare it. Well, pretty looks the same, right? Maybe it did converge a little bit more, or it has the structures more, yeah, more defined, more 1-0 design, but it also had a little bit more of iterations, right? So if you compare, so what are the results here? If you compare the lower two ones, the left one was the full model, the right one was the half model with symmetry constraints. On the left model, I said I want the result to be symmetric and have a minimum member size of 80. On the upper right here, I did not specify symmetry, but yeah, the load was symmetric, so that makes also sense that it is symmetric. But I also did not define the 80 millimeters minimum member size. So the design difference from the upper right to the lower left is mainly caused by the min member of 80. Whereas the lower two results show that you have the same results with a half model and a full model. Now, why is this so important that it's that it requires me to take such a deep look at it? Just imagine that you could save your time by reducing the model size drastically and still get valid topology optimization results. So because that's exactly what was happening here. I had the full model with X number of nodes, and then I reduced it to have half of the nodes, more or less, and have still the same results. That's pretty cool. And now, what are the preconditions that this works? First thing is you have to have a model which can be reduced to a symmetry constraint in the first place. Why do I put such emphasis on this? It's not more force on one side than on the other and reduce it to a symmetry model. That would be just wrong. So those are the things you have to take into account. But other than that, I mean, just think about having huge complicated models which with a lot of calculation time, which you can reduce that easily. So it makes a lot of sense to look into this. By the way, not only for topology optimization, it also makes a lot of sense to do this for analysis. And we did not even cover now the things you can do then for with own custom systems, because here right now it's pretty easy, as our symmetry plane was correlating with one of the global axes. But what if that's not the case? What if you have something like a structure which is somewhat circular, and you just want to have a little section here cut out? Those two boundary conditions you have then on this plane and also on this plane, they are not correlating with the origin coordinate system. They are perfectly somewhat in space. Yeah, you don't really have that. So you have to constrain that exactly in this direction only. And in order to do that, you have to do custom systems. Just imagine to have a custom system here where one of the directions correlate to the perpendicular direction to the surface. One here and one here. Then you can do that, and you have to associate the elements and the nodes to this new system. How this is done I may cover in a future video or episode, but it's pretty important. For now, I think that's all for today. Pretty content with the results. That's okay. If there's anything you wanted to ask or something you would wanted to know about Hyperworks or stuff in general, just shoot me a mail, shoot me a comment. And yeah, see you soon. Bye, guys.